Morning, everybody. Are we zombies? Yeah. 4-day weekends do that, don't they? Right? I realized just 3 minutes ago that I had neglected to post the exam topics for you. This is not something I did on the first exam because there was plenty enough to worry about, but on this second exam and the exams moving forward, I will throw up an announcement that just is my topics list when I originally generate the exam of what's going to be on it. I've got 7 questions. I can't get everything, but I can get sort of the highlights here, right? So we'll go over this here in a second, but that announcement like literally just went up 4 minutes ago. So make sure to catch that. When's chapter 6 homework due? Tomorrow, right? Okay. And then we have lab tomorrow on centripetal acceleration. More on that in a bit. And then the exam on Thursday, right? And the feeling of the freight train, right? Just this trundling along and not stopping. Wait, stop, let me catch up, right? It is happening. So the plan for today is review, but let's just kind of warm up our physics muscles just a little bit by going over this topics list and seeing if we can't pull some information out about the kind of things you're going to be up against on the exam. Then we'll get to your questions, which for many of you I know have to do with chapter 6. Especially since there's 19 of you that haven't studied it yet. All right. Sometimes, I mean, I don't do this, but like sometimes it might be nice to try to kind of figure out maybe which chapter these things come from. Just again, kind of give you a little bit of an orientation as to where to study and all that kind of stuff. So centripetal acceleration. Anybody remember the chapter number for that one? That was 5, wasn't it? All those circles, all those orbits, vertical loops, all that kind of stuff, right? So this is a chapter 5 thing. So we'll put a 5 on that. Conservation of energy. That's 6. That's what we're working on now. Inclined plane, like that. It's pretty generic. What I meant there was Newton's second law, inclined plane, right? So this would be a chapter 4. 4th thing right there. Newton's laws conceptual. Again, where did we hit Newton's laws? That was chapter 4. Orbital mechanics was in chapter 5. Power was in chapter 6. And static equilibrium, that's chapter 4, I think. Is that right? Yes. So what's the breakdown here? Looks like we've got from chapter 4, we got 3 questions, right? Chapter 5, we got 2 questions, and chapter 6, we've got 2 questions. I know how much you guys love the conceptual question last time, right? So I made sure to throw another one on there. I always give one conceptual question, at least one conceptual question per exam. And it can be difficult, right, to know how or what to study, because you just really have to know the ideas and be able to apply them. I give you conceptual questions on the homework that I know a lot of you, based on the time it takes you to do a conceptual question, you click one answer, it goes red, you click the second answer, it goes red, you click the third answer, it goes green, and you're done, right? So make sure to go back and understand, right, what the answer to that, right? It's not just something to get points for, but I'm trying to prime you and get your brain ready for the conceptual question that will be on the exam. You'll want to, it's Newton's laws conceptual, so this is first, second, third law. Third law was the song. There isn't much conceptual to the second law other than more force equal more acceleration kind of stuff. And then the first law was all about inertia and things wanting to keep doing what they're doing. So beyond that, your preparation is to review those laws, those ideas, and more specifically how they're applied. Right? How does Newton's third law tell me what's going to happen when objects interact? What does Newton's second law tell me about how the motion's going to change? What does Newton's first law tell me about what an object wants to do or not do? Right? Those are the applications there. All right, beyond that conceptual question, do you have any questions about what I mean about these topics? Like you're unclear as to either the type of question or anything like that? And it's your first time seeing them, so. When I say orbital mechanics, do you know what I mean? So orbital mechanics is Kepler's third law, things going around in circles. We did the Proxima Centauri B problem in class, and I'm pretty sure I gave you a homework problem that's got something orbiting around another planet and finding planet's mass and that sort of stuff. Those are all orbital mechanics. Kepler's first and second laws, the first law being like the elliptical part of the orbit, right? And where things go faster, where they go slower in orbits. So again, kind of a broad topic, but it does encompass a lot of stuff that came out of chapter 5, didn't it? Conservation of energy we're doing right now. I hope you're sick of inclined planes by now, right? They seem to be all over the place, but they are a very useful thing to make sure you wrap your brain around. Other than that, I think those topics are pretty straightforward. Again, remember, inclined plane, I'm very specifically meaning like a Newton's second law problem. Okay. I will warn you that sometimes on these exams it can be difficult, or like you look at a problem and maybe it has an inclined plane in it, right? And then I ask you for how fast is the thing going at the bottom of the inclined plane. If you're being asked for how fast, it's probably energy. Like 95% of the time, you're going to want to use conservation of energy to do that. Because remember, Newton's second law doesn't tell us really anything about how fast. What can Newton's second law tell us? Acceleration, right? And then you'd have to go and do kinematics to figure out what the velocity is. So we did examples where in chapter 6 where there were inclined planes, but we used conservation of energy to get there. So if you don't care about acceleration or time, try energy first, right? And of course, on the exam, if you're kind of confused, right, come up and ask me, I'll tell you, right? Okay, that's a conservation of energy problem, right? That's a Newton's law problem, whatever, right? So I'm not testing your ability to figure out like what the topic of the question is. I'm testing your ability to be able to do those things, right? So maybe I should just write it. It's too late, but maybe I should just write it on the exam, like what the problem is. Great. Any questions like about the exam? What you expected? Yeah.
Oh, what about static equilibrium?
So static equilibrium, that's when the acceleration is equal to 0. So we did the example of like a mountain climber hanging off of a rope. I think you guys, did you have, wait, maybe not. Maybe this is physics 4, like a traffic light or something that was hanging from strings? No? No, nothing like that. I know I gave you a static equilibrium problem on the homework. See if I can find it real quick. But I did the example of my daughter climbing barefoot and finding the friction between things. It's basically, it's a Newton's second law problem where you set the acceleration equal to 0 because it's static, it's just sitting there. Which the engineers and physicists argue about what does that mean all the time. Because for engineers, it's not moving, and for physicists, it just means acceleration is equal to 0. Normal force, equilibrium. Yeah, this is the one I was thinking of. So that's a static equilibrium problem right there. Okay. What are your questions? What do you need to know? What do you need to ask me? Yes, so you can feel good.
Over Kepler's second law?
I can try. Kepler's second law? So the second law is equal area and equal time, isn't it? Okay. So let's get this up. That law basically, I think the picture I drew in class was, that's the sun, here's the Earth in orbit around the sun, and I've greatly, this is like top-down view, and I've greatly exaggerated the elliptical nature of the Earth's orbit. Again, these orbits are more or less circles from our, if we just look with our eyes. But when you're trying to calculate how to get places in the solar system, it's important to know that they aren't true circles, they're slightly elliptical. So Kepler's second law is somewhat strangely stated. What it says is that if you take like that slice of the orbit, like a pizza slice of the orbit centered on the sun, and then you take a different slice that has the same amount of area between two other points, then equal areas equals equal times. In other words, the planet Earth will sweep out, will go from one point to another, filling an area, triangle, part of that ellipse, and those two things will take the same amount of time. So the time being the same, okay, but the distances are different here. This is a bigger distance, and this is a smaller distance traveled around the arc, that section of the ellipse. And so for something that moves a shorter distance in a certain time, it needs to be moving slower than if it travels a longer distance in that same amount of time, right? Think about it this way. If you are driving at 30 miles an hour and your friend is driving at 60 miles an hour, who's going to go the further distance in an hour? Your friend, right? That's kind of what Kepler discovered, right? Is that the orbital speed changes depending on where you are in your orbit. And so it's stated as equal areas and equal times, which is a bit of an old timing. We say it that way because that's what Kepler said, and we honor the achievement that he did there by using his words. But we do have a more modern interpretation of this, okay? The planet is moving slower the further it is from the sun, which means its kinetic energy is pretty small, or it's the smallest it's going to be. When the planet is furthest from the sun, it will have its least amount of kinetic energy. But because it's very far or has a larger distance to the sun, it has a lot of potential energy. Remember, potential energy is based on position. Now, as the Earth falls towards the sun, okay, it's an elliptical path, so it is getting slightly closer and slightly further away. But as it falls towards the sun, it picks up speed, trading that large amount of potential energy it had way out there for kinetic energy. And so over here, close to the sun, it has a lot of kinetic energy and only a little bit of potential energy. I've exaggerated sort of the relative amounts here, but this is the idea. What Kepler discovered about 100 years before we would conceptualize of it differently is conservation of energy. The amount of energy the Earth has out there in the outermost part of its orbit is exactly the same as the amount of energy it has when it's closer to the sun. The total's the same, but we're trading between kinetic and potential. Okay? It picks up kinetic as it gets closer to the sun, and as it moves away from the sun, it trades that kinetic energy for potential energy over and over and over again. So, I guess getting to the end and simply put, Kepler's second law is conservation of energy. This is how physicists know we're on the right track. We keep coming up with the same ideas over and over and over again. The universe is telling us something. And we change how we think about those things. The central truths don't change, but how we think of them and how we apply them certainly do, as our understanding grows. Other questions? Yeah?
Can you go to number 6 in the chapter 6 one?
6. Even I might be able to remember that number. Of course, by the time I click on all this stuff, it might be gone. that's not what I wanted. This is what I wanted. Don't let you see everything. Number 6. Sled. Snow. What's snow? Okay, starting the sled changes speed. Oh, in that distance, and they want us to find the. Oh my goodness. There's a wow. Okay, so let's just start big picture. What's chapter 6 all about? It's energy, isn't it? It's conservation of energy. And so I'm hoping, beyond hoping here, right, that I can use conservation of energy to figure out what's going on. So I know this is maybe a little bit out of order, right? But I'm just gonna throw this down so that my brain has something to hook onto as I try to visualize, right, and understand what's going on. And it looks like I'm probably gonna need some more room here. So let's get this set up so that we can flip back and forth. Okay, so we got a mass, right? There's a mass right there. What's 27 newtons? It's a force. It even tells me it's a force. This 1.6 meters per second. That's a V final, right? Because what's its V initial?
0.
Yeah, it starts from rest. What am I doing here? I'm kind of making a list, right? Like not a strict list like I kind of made with the the projectile motion problems, but I am kind of going through and seeing the things that they're either telling me or giving me a number for and trying to assign meaning to them, right? And meaning in physics generally means some symbol that we're going to attach to it, right? And then this thing right here is a distance, isn't it? All right, coefficient of kinetic friction. The symbol for that's going to be mu sub k if you really want to be particular about it. All right. So, mu is involved. Is there going to be fun? Yes. Definitely. Okay. What can I? Okay. And so, if I wanted to draw kind of a picture here, yeah, my picture might be like, here's my sled, right? And it's being pulled by a 27 Newton force horizontally. It starts at rest, and then after a distance, and again, I'm kind of like maybe reinventing the wheel here, right, a little bit. But again, maybe just a picture. So here it gets at V final, which is 1.6 meters per second. So I've like identified some things. I'm not quite sure still where I'm going to go with this, but I'm trying to give my brain something to latch onto, right? I'm trying to give it, what I've been trying to model for you is starting big. Don't like dive right into what equation do I need, right? But start with these larger ideas. Is there a way that I can leverage conservation of energy, right? Because I know this is a chapter 6 problem. So is this going to help me, right? I know that coefficients are involved. So I know that when I've got a coefficient, I've got to figure out what's going on here, right? And since forces are now involved, I'm just going to do it. I'm going to go ahead and just draw a quick, free body diagram might be a strong word for this because I haven't given a coordinate system, but I've attached forces for what I think could be happening, right? As this sled moves along. Since the sled, I've drawn it moving to the right, how do I know that the friction is to the left? It's kinetic friction, right? It's sliding, and I told you, kinetic friction always acts opposite the motion. So again, we're bringing in a lot of these conceptual ideas that we had from previous chapters to bear, right, as we try to understand what's going on here. Okay, so now I'm kind of running out of things to think about. Okay, I've identified everything, right? I've drawn a picture, I think, may be right, might be wrong, I don't know. But I've got something down. How do we start strategizing when it comes to chapter 6? Like sometimes it can be hard, right? Sometimes you can get to this point and then you're kind of like, what do I do? So what do you do to strategize? Yeah, this isn't a great sign because you haven't connected the dots yet.
Don't you
Go ahead, Juan.
where it starts, ends, and zero?
Right? We need an initial, final, and a zero, right? Mr. Balogh talked about I need an initial, final, and zero. I really don't understand why, but so far Mr. Balogh hasn't led me too far astray. So maybe I should try that. Okay, so where's the initial? Here? Right? Pick something. Try it. Strong and wrong. Right? Don't be afraid to mess it up. Final? Well, it moved a certain distance and that's where it is and I know something about it, right? So it starts where it starts, ends where it ends, and fine, okay. And then some level 0 for potential. This thing's flat and level the whole time, so is potential energy going to be an issue? Probably not. Okay. Now what? I got my initial, I got my final, I got my 0. Now what do I do? The equation is whispering to you. It's whispering something.
Potential and kinetic energy.
You start going through the conservation of energy equation. You ask yourself questions, right? We got to figure out what this work non-conservative is, right? We got to figure out what the initial energy is, what the final energy is. What do you want to do first? What's easiest? Initial, final energies tends to be pretty simple questions, right? Like, is it moving? Right? Does it have height? So we'll go ahead, we'll do that first. Now, you can do it the way I do it, which is sort of in line. You can also come over here and say, okay, what do I know about the final energy, right? The final energy, is it moving? Yeah, so it's gonna have 1/2 mv final squared, right? Does it have any potential energy? What's its height? At the final point. It's 0. Why is it at 0? Because that's where we put 0, right? Like we said the flattened level with 0 height, so the potential energy is 0. Okay, so energy initial. Was it moving initially? No, it started at rest, right? So the kinetic energy term is going to go to 0, and does it have any potential energy at the 0 point? No, it's at 0 height still. Okay, well, I like that one. 0 energy, I can deal with that. Okay, so what about this work non-conservative, right? So in a general sense, what's work? Like mathematically, equation-wise. It's force times distance times cosine theta. The cosine theta there to remind us that we need to think about the direction of the force and the distance. So of all these forces, right? What are ones that have nothing to do with gravity or anything else? We have the friction, don't we? Right? We have friction. And if I write down the work due to friction, the work due to friction is going to be the force of friction times the distance this thing travels. And I've got to remember something very, very important about those two things. What directions are they? Opposites. So is this positive or negative work? It's negative work. Okay. Are there any other forces in this problem doing work that we haven't accounted for yet? The force of the pull, right? Is the 27 newtons being caused by gravity? No.
Is the little f friction or force?
It's friction. The little curly f is supposed to be the frictional force, right? So what I drew it acting backwards, right? So, but now I'm asking about the 27 Newton force. Does the 27 Newton force do work? Yes. Is it mgh? No. Is it 1/2 mv squared? No, right? This is a force that's in my problem that's doing work. And how much work is it doing? Well, it's doing its 27 newtons, right? If we call this one F, right? It's doing its 27, and how long at what distance does it do it? the same distance as the friction, and is that work positive or negative? Why is it positive? Same direction, right? Right? Okay, good. We could ask about normal and gravity. Is gravity doing any work here? No. Not only is there no MGH, right? But MG is down, and what direction is this thing moving? Horizontal, those are perpendicular to each other, right? And what about the normal force? Is it doing any work? No, again, perpendicular, right? It's the cosine theta thing, where you put 90 degrees in, you get 0. Okay, so those are all the piece parts that I've got. So let's get them all together in one place. I've got minus the friction times the distance, plus my 27 newtons times the distance. My final energy is 1/2 mv squared. And my initial energy is what? 0. Okay. I'm being asked, I don't even remember what I'm being asked. What am I being asked? Oh, coefficient of kinetic friction. Where's the coefficient hiding? In the little f, right? So now I've kind of, so again, there comes this point when we've been applying physics, like ideas and linking stuff together and trying to use math as an expression for the relationships between things. That's everything on the screen right now. Starting with that green arrow up there, what am I doing? Now I'm doing algebra, right? I'm trying to solve a mathematical puzzle. And really, physics goes on pause here. We don't need concept to solve math problems. We need all of those math classes we took our entire lives to solve these math problems, which for some of us was too long ago, and it hurts to try and think about these kinds of things. Because then it reminds us of high school, and I hated high school, I don't want to go back. So, let's see, I go minus mu nd, and then this is a 27, and this is an 8.3. I can just start throwing numbers in now. 1/2, they gave me the mass, didn't they? 19 kilograms. Times the V final, which was 1.6. I gotta remember to square that. So, looks like everything on the right-hand side is a number. The 27 times 8.3 is a number, so what do I do with it? I'm going to take this thing and I'm going to move it over there, right? Negative 27 times 8.3, whatever that is. Okay, so let's see here. The D I know is 8.3. Do I know what the normal force is? It's not 0. You want to guess some more? It's mg, right? Look at right here. Okay, math pause, physics on, right? Okay, the normal force points up, mg points down. Is there an acceleration in that direction? No, right? So okay. Technically mg cosine theta, but the angle's 0 here. If it were on a hill, right, we'd have normal force and mg tilted towards each other. But here I can go ahead and just write mg, right, and now this is an 8.3 equals whatever all this number is over here. So now to get the mu, what am I going to do? We've got to do some division, don't we? The first thing I think I want to do is multiply by -1 because I don't like minus things. And then divide by mg, right? Divide all this by mg. So that leaves me with mu equals whatever all this number is, minus 27 times 8.3, although I put minus signs for everything, there we go, all divided by my mass, 19, oh it was right there, times the planet I'm on, 9.8. So in theory, that should give me my coefficient. 8.3 on the top.
One above that, mu mg times 8.3.
Oh, thank you. I'm glad you're here, Kamari. Right? Quite honestly, this problem all went wrong when I put numbers in. I should have done it all in symbols like I normally do. But yeah, Kamari is exactly right. I have to divide by the 8.3 as well.
Where did you connect to the bottom, to the bottom?
Mg.
Oh, MG.
Yeah, the mass is 19. I won't waste your time by putting all that in and getting a green box and dancing for you, but I'm pretty sure that's it. Okay, back up. Analyze what just happened. I modeled a process for you, right? I modeled the process of visualizing, strategizing, and working it out. So the question now becomes, can you do this in 10 minutes? And the answer is, of course not, Mr. Balogh. I can't do this now. And so, what do you think, based on what you know about how the first exam went, do you think the problem will be this complicated on the exam? Okay. Less complicated in what way?
Not multiple steps.
There might be multiple steps, the question won't be like A, B, and C, right?
Or information is given to you.
Nick's not wrong. Generally, what I will do is try to make the math as fast as possible. What am I trying to find out? As a teacher of physics, what am I trying to find out? Do you know physics, right? And so do you think I expect you to be able to write out a correct conservation of energy statement for a problem like this? Sure, right? But I probably, if I was taking this problem and I was like, I want to use this problem as a template to make the exam, knowing that finding the kinetic friction involves a lot of math and breaking this thing down. Instead, I might focus this problem more into, find the work that friction does. Right? And then you just need to do 1/2 mv squared and the force times the distance, and you've got the work that friction does. There's ways for me to shortcut the time it takes to do a problem, but still see if you have the physics understanding there. And that's a lot of what happened on the first exam. And some of you came up and complained. I won't name names because I don't want to embarrass you, but I know I've done something right when students come up to me and complain and say, Mr. Bailey, exam is too easy. And you're like, who said that? I'm going to kill him, right? And I said, well, what do you mean it was too easy? And they're like, well, I overcomplicated the problem. I thought the problem couldn't have been that easy because we had all of this terrible homework and all that kind of stuff, right? This is with me saying that my goal on the exam was to make it medium level difficulty, right, the whole way through. So I guess what I'm trying to communicate here is this exam is going to be hard, but I have tweaked it so that you're spending little time on math and more time on setup and all that kind of stuff, right? And if you're going to focus on something, focus on getting the problem set up. After the exam autopsy, you kind of know if you got it set up, that's at least a point there, and maybe even 2 points. If the setup is correct, but your answer is wrong, I might be like, algebra mistake somewhere, I could care less. So remember, you got to be able to do something like this in 10 minutes, but I've engineered it so that is definitely doable for you, right? Not for me, not for the other physics teachers. I hope that helps you feel a little bit better. If you can do this, if you understand what happened here, I'm not going to panic for you about the conservation of energy question that you can do on the exam. What?
So for chapter 5, there's a lot of forming your own equations.
Yes.
But from what I've noticed, there's some where it helped me, like, we went through an example, and at the end, we got an equation.
Yeah,
And instead of going through the whole process, for one of the homework questions.
you can just use that equation, right?
Is that?
Yeah, totally, right? We developed a toolbox in chapter 5 for finding things like orbital velocity, the acceleration, little g on the surface of a different planet, right? You don't have to rederive those things to do the problem. Now we know, right? And let's see if I can even remember. This is totally off the top of my head, so I'm gonna have to go back and check these things. But I think, wasn't this little g? That came out of putting Newton's second law and Newton's universal law of gravitation together and seeing what the implications were. Oh god, I think, no, Gm over R. Mr. Balogh should never be allowed to teach anything having to do with equations without his notes. Because I can't remember, equations don't stick. That's that chapter. Right chapter. Yes! Nailed it. Okay, those are correct. It's an absolute miracle. I'm going to take that as a win. Okay. Again, we found that V right there. That's an orbital for something that is in orbit. That's the orbital speed it's going to have if you know the distance from that object to the center of the thing being orbited, usually a planet. So we got that. I probably showed you how I got that. You don't need to redo that. This is like a toolbox equation, right? It's a generic result. If we're orbiting Pluto, what mass do you put in there? Pluto's mass. If we're orbiting the sun, what mass do you put in there? The sun's mass, right? It's the thing being orbited. What was the other one we came up with? I don't remember. I think that was for orbital. Well, the other orbital mechanics equations are Kepler's third law. Gm r to the 3 halves, I think is how your book wrote it. And then this one's more generic. It's part of the orbital toolbox, but that's a basic definition for anything in rotation. So, but yeah, Juan, you're right. You don't have to reinvent the wheel. You use the tools that we developed. Yeah.
So one of the homework questions, how does use the equation V equals square root of R times G?
Yeah, okay, so that one, the square root of R times G, was for a turn, a banked turn,
Something like that.
water skier, something, right, okay? So yeah, so that's, again, the result for, I think if there was like no friction or something like that, okay? And I think there's a result for, we're gonna do tomorrow in lab. Tomorrow in lab, we're gonna do a problem where a car is going around horizontally, right? And we'll figure that out. But anyway, so it's a, how am I going to say this? Equations. So we started this semester with the kinematic equations toolbox, right? I never showed you where those equations came from and all that kind of stuff. In this unit, I've been showing you more of where the equations come from and developing these relationships that apply not just a single example, but can apply to many examples, right? Again, building up a toolbox, right? Taking a little bit more, showing you a little bit more behind the scenes of what physics is all about. I am a physicist and I enjoy figuring out how to put things together to get these results that we can then apply everywhere. I know you don't take the same amount of enjoyment as I do out of things like that, but yes, you can use these equations, right? Just make sure, just like the kinematic equations, that these equations are applied to the correct situation. And this is where I've been begging you over and over again to start big, start your thoughts way, way out, conceptualizing a framework. Is this a conservation of energy question? Because if I can figure that out, then I can figure out like the toolbox that I need for that. Or is this an equilibrium problem? In which case there's a different set of ideas that I want to focus on it. And how do I tell the difference? Like, how do I know if it's energy versus static equilibrium, right? What are the things that are a giveaway for static equilibrium? An object is not accelerating. And they're asking you to find like the force of something, right? Now, you can have a conservation of energy problem where there's no acceleration, but it's probably going to talk about the speed that the object has, right? And then the forces that are involved. You're like, well, Mr. Balogh, both of those have forces. Yes, they do, because energy is all about work, and there's forces in work and all that kind of stuff, right? But the emphasis of what you're being asked to find in the context of what you are being given is so essential for figuring that out. So like for me on cheat sheets, like one of the golden things is, how do I know? Like I make myself a list. How do I know that it's a static problem? How do I know it's a conservation of energy problem? How do I know it's a centripetal force or acceleration problem? Right? You gotta be able to contextualize these things. So it's a big ask, right? You got, not only do you have to learn this stuff and study to learn it, but then you also have to take a step back and say, what the heck have I learned? And summarize the information that you've been given into these toolboxes. The three major toolboxes are Newton's laws, things going in circles, and energy. So, yeah, physics is hard, isn't it? It's hard. It's doable. You can be successful at it. You will be successful at it. But it's hard. All right. Dad mode off. Other question?
The cheat sheet is 1 page, right?
1 page, front and back. More of a safety blanket. Yeah.
What day is the exam on?
The next time, not the next time, the week tomorrow. Thursday.
This Thursday?
Yes. Right here, right? The room of doom. Yeah,
You can go over number 11 on chapter 6.
I can try. About lab tomorrow. There is going to be time for grasp. Grasp type, like stay and, you said 11, so it's fine. And so you can come tomorrow, we'll do lab stuff, and then there'll be time for you to work on homework and things like that, right? So take advantage of that. This doesn't affect you nearly as much as my Physics 2B students, but this Friday, GRASP, which you're probably not going to go to because you will have just taken an exam and the last thing you want to do is think about physics and you probably have to catch up on all your other classes. GRASP is not going to be held. My office hours are canceled. GRASP will be over in the tutorial center. The tutors are running GRASP. All the faculty on Friday, we are involved in Women in Engineering Day. And so we're going to be hosting a bunch of high schools here. Got a lot of women coming, and I'm helping with all of that. So, and all of us are. All the engineering faculty, all the physics faculty, that kind of stuff. So GRASP won't be here. It'll be over in the tutorial center. There won't be any faculty over there. You really don't have to worry about it. Don't come to GRASP this Friday. But I am going to make sure that you have time tomorrow for GRASP to ask me questions. My office hours canceled on Friday, so my office hours in effect will be in lab for you tomorrow. Right, so. Sarahi, you said number 11, right? Oh, water slide. Okay, what does this water slide look like? An inclined plane, right? Okay, and even if it doesn't look like an inclined plane, that's kind of where I'm going to start because I don't want to think about anything else, right? And actually, for conservation of energy, it doesn't care if it's an inclined plane or a loop-de-loop or anything else. Okay, slide it on the way. Oh man, kinetic frictional force. Student has mass, height, kinetic how, okay. So again, starting big, thinking big. Get this ready to go like that. Back to here. I know it's conservation of energy because it's in chapter 6. But how would I know it's conservation of energy if somebody was just asking me this? Does it want to know anything about acceleration? No. It's also, I mean, it's not telling me anything about forces. I know forces are hiding in there somewhere, because they always are. But since it's not really telling me anything about forces, and it's not asking for acceleration or how long it took, I'm going to give conservation of energy a try. Right? And again, I'll just write that down, not so much as something to play with right now, but to give my brain an anchor for how I want to conceive of this question. Okay? So I need to have some sort of picture. I'll just draw the inclined plane like that. What did they tell me about this thing? It's 11.3 meters high. Usually in a physics problem, when they tell you something is such and such high, they're talking about the vertical height. We'll say something else if we know like the distance, the total length of the water. Did they give me the length of the water slide? No. They just gave me the height of the water slide. Okay. This amount of work right here. Okay. Where's that go? Work non-conservative. How do you know that? It tells you it's a non-conservative force, right? Okay? And so they just gave me my non-conservative work term. This is great. Fantastic. Okay, so we know it's that high. We know the mass of the water slider, and we know the work non-conservative. So let's get this over here. This means I need an initial and a final. We'll do initial at the top of the slide. We'll do final at the bottom of the slide. We'll put 0 at the lowest point in the problem. Okay, is there work non-conservative? Yep, given to me, so I'll just keep writing that as work non-conservative for now. 2 questions at the final point. What are the 2 questions we ask ourselves when it comes to energy? Is it moving? What's the second question? Where is it? Right? Or what's its height? Okay, so is it moving at the bottom? Yeah, as a matter of fact, they're asking us to find what that final velocity is, right? Now, does it have any height at the final point? Nope. And why doesn't it have a height? Because that's where we put 0. So minus 0. So now minus, and we better put a big parentheses here. Initially, is this thing moving initially? Starting from rest. Code words for no kinetic energy. So the kinetic energy is 0 plus, and now, does it have height at the initial position? It certainly does, right? And since it has height, we're going to go ahead and write mgh. All right. I may not have everything yet, but let's just take a step back here and see what is it that we know. Do we know work non-conservative? Yes. Yes. Do we know the velocity final? No. We know the mass. Do we know the height? Yeah. So everything except the velocity final is a known quantity, isn't it? And they're asking me for velocity final, aren't they? How fast is the student going at the bottom? Okay. So I gotta solve for velocity final. So first thing is I gotta move the negative mgh over. So it's work non-conservative plus mgh. It's a g. Equals 1/2 mv final. So this minus sign went in, right? It's negative mgh, and so I add mgh to both sides. Okay. And then I multiply everything by 2 to get rid of the 1/2. And I divide everything by m to get rid of the m. And then I square root everything. Why is it happening so fast now? I'm just doing algebra. Non-conservative plus mgh. So now I can just put in all the numbers. I'm not going to do it. But like that negative, it's important, right? They gave us the work as negative 5.9 times 10 to the 3, right? So that negative sign's important. It's kinetic friction, it's doing negative work. I'm just hoping that MGH is bigger than that. Otherwise, I'm gonna end up with a negative number under a square root, and then I'll be doing imaginary physics, which is fun and all that, but not real. Yeah. 100% confident that's gonna work out. Having been here before. Come on now.
When you get to the second equation where you said 1/2 MVs, all that stuff, why did you do the parentheses with the kinetic energy?
Right here?
Yeah.
Okay, so what's going on right there is I have it's work non-conservative equals energy final minus energy initial. Both of these energies are combinations of the total energy at that point. So minus kinetic energy initial plus potential energy initial, right? Energy initial is all of this. Energy initial is kinetic energy and potential energy initial. But when we do the conservation of energy, we're taking a difference, right? It's final minus initial.
So you plug in what kinetic energy equals and okay.
Yeah, and there kinetic energy was 0, but potential energy wasn't. But the minus sign has to come through, right?
Yes.
Mathematically. Math is magic. Having never understood it myself. Yeah.
The height correlates to the potential energy.
Yes. MGH.
That wouldn't be the same for horizontal.
No. Horizontal distance usually ends up in work non-conservative. Yeah. Right. Or even if something's sliding down a hill, that would be a D and an H. Right? But yes, you're pointing out something that's very important, right? We've taken care of the work done by gravity. It's MGH, right? Which is why when we're in that non-conservative and we're asking that question, is there anything besides gravity and kinetic energy that's going on here? If you got another force doing something, you gotta make sure to include it in that trash bin of work non-conservative.
Why do you have it as 2 and then parentheses and one inside? Why did you put it 2?
Third line down.
Yes.
I had a 1/2 MV final squared over there, and I wanted V final all by itself. So you multiply everything by 2. So it's 2 times everything, and everything was work non-conservative plus MGH. And then divide by M. Yeah, I was just trying to get rid of that 1/2. Yeah, sometimes it's like 2's appear mysteriously, right?
How come it only divides the, M only divides the 2, but not the W and C?
It is dividing, that's what parentheses mean, right?
Oh,
Right, that parentheses, I do what's in the parentheses first. I get a number, multiply that by 2, divide by M. That would be exactly the same as if I divided each term by M first, before adding them together. It's just, in math, you can use parentheses to save yourself a little bit of writing.
Going over a orbital problem? Any one?
I mean, SpaceX is gonna try this week or next week, why not? They're launching their big rocket, maybe 3 weeks from now, I can't remember. Thought they announced the launch date, but then something else happened. Anyway, do you have one in mind, or
No.
if I make one up, it's gonna be dangerous?
You did chapter 5, number 11.
Yeah, is that an orbital problem?
I don't know. I just have a question.
Okay. Actually, I will answer your question. So you said 5 number, let's see what 5 number 11 is. And then we'll see if we have to pivot. Looks like this is an orbital. I am gonna punt on this one because it's from chapter 5. You can go see the solution in here, right? The instructor solutions manual. If I get time, I'll go over it. But let's answer Ashley's question about orbital stuff.
Could you do the one on the?
Try. That's probably the safest bet, because if I make something up, usually what happens is if I make something up like on the fly live, it ends up being really difficult. Because what's fun for me are hard problems. And for you, not having a problem at all would be much more fun. It's chapter 5. Do you know what happened there? When I do orbital mechanics, I start with energy. I forget in physics too, we leave it. We don't do orbital energy. It's too bad. All right. Apparent weightlessness, artificial gravity, banked curves, and triples. So they're not. Let's do. That's not orbital. This one is. Want to try this one? Want me to explain it? Solution is available there, right? So let's do this and then I'll see if I've got time to go back and explain the other one. Oh, satellite. Okay, so as soon as I got the word satellite, I'm starting to think, get this, there we go. I'm starting to get a sort of like this picture in my head, right? Of some big mass, right? And then a satellite, which looks like a TIE fighter, is going around it. So I've just got this picture in my head, right? For about every orbital mechanics problem, even if the satellite's doing a weird elliptical orbit, this is always the picture I start with. Okay, we got mass, and it's in an orbit that far above the surface of the planet. Uh-oh. Above the surface of the planet, what is this number? Is this the orbital radius or the orbital altitude? Its altitude is being measured from the surface of the planet. 4.9 times 10 to the 5. So what they gave me there, the red distance, is not an R, it's an altitude. 4.9 times 10 to the 5 meters. Okay. Period is 1.6 hours. So period 1.6 hours. And and then they gave me the radius of the planet, I have to make them so the same. So radius of the planet, that's this to here. This drawing apparently is not to scale because the radius is 10 times bigger than the, anyway. This radius of the planet, 4.55 times 10 to the 6. This is all visualization. It's an organization of information. It's getting definitions down for various things. Trying to organize my thoughts, right, around the information that's been given to me. You do it wrong a lot, and as you do it wrong, you learn how to do it right. True, okay, they're asking me for a weight. I know that weight's equal to mg. They gave me the m, so this means I need to find the little g for the surface of this planet. Is there anything in my toolbox that gives me little g when I'm on the surface of the planet? Yeah, I remember writing this equation down earlier. Gm over r squared, right? We know big G, it's a constant. Do we know big M? No. Well, they haven't given me anything about the mass of this planet. But they did give me a period, and I've got some distances, right? And so that's sounding a whole lot like the dreaded Kepler's second law with that 3/2 thing in it, right? So, what do I do with the period first to fix it? I gotta get it into seconds. And some of you have been pointing out that yes, surprise, surprise, I made a mistake in one of my calculations. on one of the examples, I think I said that the period was 5,667 seconds, but it comes out to be 5,654 seconds. I don't, it's a number up. Yes, I was off a little bit. I'm a physicist. I can be off a little bit. So 1.6 hours, and in 1 hour, how many seconds are there? 3,600 seconds, right? 60 minutes in an hour, 60 seconds in a minute. 60 times 60 is 3,600. Okay, so we figured out what that is. The R that goes into here. Which of those R's, which of those R's over there do I put in? Both of them, right? I need the distance from the center of the planet to where the satellite is. I know the distance from the center to the surface and from the surface to the satellite. So my R is going to be the combination of the altitude plus the radius of the planet. The altitude, 4.9 times 10 to the 5th meters. It's supposed to be a 5. Okay, plus radius of the planet, 4.55 times 10 to the 6th. Both of those are in meters, which is good. That's exactly what I need them in. So now I've got that R. I can solve this for the big M. It's going to need to be a little bit of algebra. I think I've done this in class. 4 pi squared over g m r. And when I square both sides, it gets rid of the 1/2 from the R. And then just solving for the mass. G period squared r cubed, right? So I can find the mass by putting in my R and my period in seconds. Once I've got the mass, goes in there, which gives me the little g, and once I have the little g, goes in there to give me the weight of this thing on the surface of the planet. Again, kind of went fast there and didn't do all the math to make sure I got to the next question here. Ashley, did I do you service with an orbital problem? Biggest trip ups in orbital problems are not getting that distance right. Because it is kind of changing, right? Where am I? Am I on the surface? And the radius right here, this is the radius of the planet. Why is it the radius of the planet? We're trying to find the weight on the surface of the planet, right? So we want little g on the surface of the planet to put in for the weight on the surface of the planet. So yeah, keeping track of the different radii, confusing. It is. All right, and then the horror that was the last problem. Frozen shoulder, stiff shoulder, this orbit right here as this thing goes around, okay? Since we are a little bit short on time, let me just show you how you can take advantages of the key being posted, right, after the homework is done. Especially as you come in with a question, that kind of stuff, right? You're like, okay, I didn't do this question, what's it like, right? Okay, so here in the solution, they are giving us this is what I would see, right? If I go to the instructor solutions manual and I pull up how do I do this problem, it's exactly the same thing, right? So not all the time is it clearly spelled out, but as we can see here, their approach was to draw a free body diagram of the mass hanging right down there. And it's like, well, but the problem up here, right? All it gives me is a period, the 1.2 seconds, right? And a mass. Like, how was I supposed to know that I'm supposed to use force? Well, number one, it is a chapter 5 problem, right? So it's kind of a dead giveaway that forces are involved. This thing's moving in a circle, so centripetal acceleration and forces are involved. And so drawing a free body diagram isn't a bad way to start figuring things out. Okay, so in their free body diagram, what have they done here? They've got a tension, and then they've got like a Tx and a Ty. What are they doing? Well, yeah, they're finding components, right? Tx and Ty are components. Why are they finding components? What's going on here? The circle is a horizontal circle, isn't it? So is the vertical part of this tension going to do anything to affect that circular motion? No, that's not the direction the circle's going, right? So they're saying, look, let's try to find the force that's pulling this thing into a circle. It's a centripetal problem. The force that's pulling it into the circle is the tension. It's just not the tension, the full tension. It's the part of tension that points towards the center of the circle. We've got an angle of 47 degrees, right? And so to find the Tx there, right, with that 47 degree angle, sine or cosine? Sine. How do you know? It's not touching Tx, is it? It's touching the vertical and the, what's the longest side of a triangle? Hypotenuse, thank you. Okay. I had a good weekend. I also ran 10K yesterday and I don't feel like living anymore, but that's okay. All right, so I'm going to use sine. Tx is going to be T sine theta. I've got my R. Okay, so what else is going on here? So they're setting up this centripetal force, the thing that's pulling it towards the center of the circle, has to be that. Again, a centripetal force is not a new force. It's just a different name for a force that's already there. The force that points towards the center. So they come along and they go, okay, what are they doing here? Tx, right? Oh, and what happened here? Okay, this looks like Newton's second law. F equals m, and then this is an A, isn't it? How do I know v squared over r is an acceleration? Centripetal accelerations that point towards the center of things, right, can be found if you know tangential velocity and the radius of the circle. Okay, so they didn't really say it. Did they say it in circular? No, they just plopped down Newton's second law without writing down Newton's second law first. Okay, fine. There's the sign. I was right. Okay, equals that, right? And so now, right, they gave us the time it takes for this thing to go around, so that means we can find the velocity. Looks like we're going to need to do the vertical equation to be able to find out what the tension is. Oh, tension cancels out. Yeah, and then they do some mathy stuff, and then they use the period. This is the equation for relating velocity, period, and circles. Things going around, right? And then they put it all together. I know it looks like a lot of math, but really they're just sticking things together as symbols to finally come out with the distance. So it turns out like a problem that seems sort of simple on the surface can kind of blow up on you, right? But in the end, it gets down to an answer, right? And yes, I've had to do this in physical therapy. And what was I doing while I was swinging a dumbbell at the end of my arm? Thinking about the forces that were involved. What are you going to remember today, tomorrow, and Thursday? It's one of the most important things that you need to remember. Yeah, I knew you already forgot about it. You deserve to be here. You're like, what part of the book? You deserve to be here. Okay? And I know many of you feel uncertain and scared, and I have no idea what's going on, and I can't possibly pass this class, and blah, blah, blah. No. Okay? Don't listen to that voice. Okay? You deserve to be here. You fought for this. Hard. Keep fighting. Don't give up. Keep pushing. If you feel yourself wanting to give up, reach out to me, right? Let me help you. I can help you. But remember that you deserve to be here. Take a stance of power, not victimization, right? You deserve to be here. Move forward. grab it by the horns and don't let go. Just keep working. Whatever you need to do, sacrifice time so that you can study, do it. It's worth it, okay? It's gonna pay off in the end when you pass physics and you're able to go on and do the things that you truly love and enjoy. I will see you tomorrow. Come tomorrow knowing that you're gonna have time to spend on homework and to answer any questions you need for Thursday. There will be time, I promise.